Hey everybody, can you see and hear me? Let's get started here. What questions are there? If everyone can see and hear me, what questions are there? It looks like you can see and hear me. So let's hop back over to Word. Let's do that. Ask those questions. Number 3 on the practice exam. I think I still have the practice exam open right here. So let's go over to number 3 on the practice exam. You asked first, you get the question. So number 3 on the practice exam. Where is that number 3? Here it is right here. Is this number 3? Oh, is it? Are you talking about which one right here? Can you repeat to me? Is it, here's 3. Which one is it? Decision tree is your word. We could do decision trees after this again. Which one is it? Andrew asked first. Please, number 6, part 6 on the exam. First page. Okay, first page. This one right here? Are we talking about this? Whoa, craziness. So is this the one right here we're going to do? We got time for like 3 or 4 questions right here. So this one right here. We have that we are going to have a fair-sided coin, With this fair-sided coin, it's going to be 50-50. On this question, I'd probably write out probability of heads is equal to 50%. Probability of tails is equal to 50%. Always be taking notes. Always be putting stuff on your exam. Can you do the last question of the practice exam that aren't in the review videos, please? There should be review videos for them. We'll try to do those too here. Can we talk about the 10%? Oh yeah, we'll talk about more here. So we'll do these. We'll take all these questions, as many as we can. So if the first coin flip comes up tails, what is the probability that the first 3 coin flips come up tails? So it's saying you get tails, then you get tails again, and then you get tails again, and then what is the probability the next one comes up tails? So here's the thing. This is not the law of averages, because when you flip a coin, it doesn't matter, and Mona Lisa got it correct right there, it's still 50%. It doesn't matter. Like these events in the past don't tell us anything about the current event. The probability of tails is still 50%. Because it's like your friend's like, oh, you flipped tails 3 times. You're going to flip heads now. It's like, no, it's a fair coin. The question assumes that it's a fair coin, so it would still be the probability of getting a 4th flip coming up tails would still be 50%. It's not saying you get 4 tails in a row. This is not the answer to the question. This is a side answer here. I'm going to put this over here to the side. This is not an answer to the question. But the probability of 4 tails would be 0.5 to the 4th power. The probability of 3 tails would be 0.5 to the 3rd power. So it's behind my head now. But those would be the associated probabilities with those. And that's not the answers. I don't want someone to like take a screenshot and be like, he said it was 0.5 to the 4th power. Do you still need 0.5 or it's 50%? Either or is fine. Those answers would be correct. I'm going to try not to block it. But the graders should know to count both questions right there. And we can do that too. We're going to try to get through as many things as we can. You guys are studying hard. I'm going to try to do as many questions as I can. What is the probability of getting 5 tails in a row? Oh, we just did that. That means we got tails, and we got tails, and we got tails, and tails, and tails. Did everyone hear that word I'm saying between all these? I'm saying and, because the coin flips are independent, so we'd get 0.50 to the 5th power. And that'll just solve out to be 0.5, 0.25, 0.125, 0.125, 0.0625, and this is equal to 0.03125. Please tell me if I'm wrong. I'm trying to do it in my head right now, just trying to think through it. But and they're saying it, Mona Lisa, thank you so much. Mona Lisa is confirming our answer in the chat. This is the correct answer. I was just doing halves of halves of halves of halves of halves. Put in your calculator to check. It's fun to do it in your head, but if you have a calculator, double check it. So we just did 0.5 to the 5th power because you get a tails and 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 a tails. Suppose we have 2 events right here, event A and event B. What is the probability of A or B? Here's some keywords right here. And what do we notice? They are disjoint. What can we do with 2 disjoint events? We can easily add them together. And what does it mean for 2 events to be disjoint? If 2 events are disjoint, it means if one happens, the other can't. It's kind of like the idea of here's A, here's B. This is disjoint. But not disjoint would look like this. Because what am I showing you with not disjoint? There's an overlap between A and B happening. So that graphic where they're overlapped is not disjoint because, and great job Mona Lisa in the chat giving some answers, A and B having an overlap is not disjoint. When they don't have an overlap, that means disjoint, which is the same thing as mutually exclusive. So this probability right here is the following. And then we have right here A and B, which is independent, is the rule that it has to be met. What does independent mean? It means if you know A, it tells you nothing about B. I want you to think about this. Is snow and having school independent or dependent? How would you ask that? You would say, is having school dependent on snow? Would having school depend on having snow, or is it completely independent of snow? Like having school is independent of snow, or it is dependent. Tabs, you are right there. It is very dependent. Now this question explicitly says that they are independent, so we can multiply them together. And we ended last review session by writing out our notes on this. Well, all we have to do if we know the probability of A and B is just multiply. So we're just going to multiply these two probabilities right here, and we would get I believe it's this right here. Please correct me if I'm wrong. 3 times 8 is 24. Move the decimals around a little bit, and you get 0.24 is the probability. And we can multiply these because they are independent. And if you notice, I'm trying to connect these words right here, that if you want to add, the addition rule right here is the word or, and they need to be disjoint. And then the multiplication is the and word. And to multiply, they need to be independent. Nice job with the notes in the chat. Keep it up. And am I doing it incorrect? Oh my gosh. Wow. Oh, you know why? Thank you so much. I was looking at the previous probability. You're one of mine, right? You get 10,000 points for that. I looked wrong way and saw that and grabbed a wrong probability. Nice job, Cindy, right there in the chat. Busted. Oh no! The probability of A is 0.3 and the probability of B is 0.5. So this is really just, when you look at it, and that was the wrong answer I grabbed right there, because all we're doing right here is the probability of A times the probability of B, and I went and grabbed the probability of the wrong thing. So that can happen. Be very careful, double check your work. We're all capable of these little mistakes. You can know the concepts and then make a little error like that and be like, no, I grabbed the wrong probability. Oh, it just gets me. So good stuff. Cindy, nice job. And I see Keaton noticed it too. Great job. People in the chat are like, wait, you grabbed the wrong probability. And please note, the probabilities are right here. Where did Brian get those probabilities? It explicitly says them in the problem. Make sure you grab the right ones and do the math the correct way. A lot of people ask about this last question right here. We have events C and D. So these are new events, and we're going to give them names. Event C is that you get to work and you get rear-ended along the way. So you got rear-ended on your way to work. Event D is that you made it to work without getting into an accident. Now I want you to think about this. Can you make it to work, like you get to work and you're like, I made it to work without getting into an accident, and then someone's like, but I heard you got rear-ended. You're like, well, I got rear-ended, but I didn't get in an accident. Can you make it to work without getting in an accident and make it to work and have gotten rear-ended? Like without getting into an accident and also make it to work without getting into an accident? No. So what's the probability of these two things occurring? And it's interesting because what we have here is we actually have disjoint events. So what amount of time does A and B occur? What amount of time does A and B occur? A and B occurs 0 amount of time for disjoint events. Because if A occurs, B can't occur, so A and B can't occur together. Does that help make more sense of this one, that you can't get into an accident and not get into an accident? And it's weird, you might say, why don't they add up to 1? Because maybe it's like you got into a fender bender or you got into like a major accident, and that'd probably be like probability of event E is like major accident. Like it says rear-ended on the way to our work. We could say event C is you get into a major accident, and now we have the set of all events. You will either get into work without getting into an accident, or you'll get to work having gotten into an accident or get into an accident on the way to work. One of those things must occur because it's a complement. So when are events mutually exclusive? You can't have two mutually exclusive events occurring. This question was one of the ones people always ask about because it's a good kind of tricky one. If events are mutually exclusive, the probability of them both occurring is 0. Can you make an A on tonight's test and an F on tonight's test? So think about this. Can you make an A on tonight's test and an F on tonight's test? So the probability of an A, we got some good grades in here. The probability of an A is 40%. Probability of an F is 2%. So what's the probability you make an A and an F? What is the probability, and if you take it twice, that's a different problem. What is the probability on the test tonight you make an A on this one test and an F? The probability would be 0 because there's no amount of time that you make an A and an F. Does that make sense? You can't make an A and an F on this one test tonight. So those are disjoint events, And on disjoint events, if one occurs, the other can't. So they can't both can occur. They can't both occur. So the probability of A and B right here is 0. I think there was, what are the other questions? I think a bunch of people had questions. Say your questions if you had them. I know people are like, cover this, and we're going to try to cover everything we can. Sorry if I'm going quickly. I'll try to slow down, especially if you're in the chat and you're like, hey, slow down. I'll slow down. Number 6, part 4. Where's number 6, part 4? If you tell me what the question is, I'm usually better at finding it that way. Is it this one? I don't want to write all the simulation. I know, I love writing the simulation out as much as you guys do sometimes, like when you write everything out. Is it this one right here? With the number 6, this looks to be number 6. And this is a great question right here, I think. This is an amazing question. This is one you want me to do, because we're going to point out some, number 6, part 6, this is the whole question right here, right? I'm going to point to some major learning objectives that we should know with this question. This is the question, right? Because we're going to do some learning objectives on it. Cool. Here's the learning objectives. When you are taking the test, you should see keywords like this. Boom. That is drawing you in right there. Once you see this, I would go right to my formula sheet, and on my formula sheet, that's page 7, we'll remember that. What do I see right here? Sampling distribution of p hat. That's what that just said, what I highlighted. So I just found out that I need to be using all of these equations right here. These are the equations I will be using for this problem. Also, since it's p hat, I know my third condition now if I get asked conditions. This question right here is success failure. This is large enough n. And this one down here, which you can barely see, which is a confidence interval, is also success failure. Sorry, I converted it to PDF and this formula got destroyed. That formula is p hat plus or minus z star, that's a star up there, and then p hat q hat over n square root. I converted these to PDFs and it destroyed part of the formula. I don't know why it did that. Converting to PDF wasn't happy with this. So these are the conditions right here. Success failure for sampling distribution of p hat. Sampling distribution of y bar is large enough n. My head's blocking the way. And then one sample proportion confidence intervals is also success failure. So we know our conditions and we know when to apply them. And if you remember, I know what I'm doing because right here, what do you see? Sampling distribution of the sample proportion. So we'll just zoom in a little bit here. If you've done this problem, which I hope you have, remember there's review videos for all these, and there's also the review test. And sometimes we add extra videos on to just put extra things onto the review test because it's hard to cover everything in videos and everything, but we try to add them on there so you have a bunch of different examples to look at. So what do we have right here? The sampling distribution of the sample proportion is what could possibly happen in a sample size of 50. When we're doing this right here, we're talking about the possible distribution of the amount of water heaters that would still last after 10 years. That's what this question is getting into. The proportion of water heaters, I think A and C both could be correct. C says the distribution of all possible sample proportions for all possible, here's the part that's wrong on this one. That. Theoretically, you could use any sample size, but it would change it. This question right here is specifically for a sample size of 50, because what will change for this will be the P times Q over N square root. And since N is used in the equation, we have to be talking about for a sample size of 50. Since N is used to make the standard deviation, then this sampling distribution that we're doing right here refers to a specific sample size of 50. And feel free for clarification on the test, like, are you talking in general or are you talking about this question? And we would say, like it says, in this example. So that's kind of the key right here. In this example, it's for a sample size of 50. That's the key thing right here. If you know how to do the practice test, you are doing great. No decision trees too, and you'll be doing great, which we do have the video for that. Condition 1, people were asking about these conditions a little bit here. Let's talk about it. 1, what is the first condition? You should know these pretty quick like now. And what is condition 1? We won't flood the chat too much. Condition 1 is random, and what do you see right here? We say they go to a random sample. Look at that. We're going to highlight a random sample. Condition 1 is random, like Dylan remembers that from the last one. Condition 1 is random. Yes, it is met because these are a random sample. What would you write for condition 2 right here? Condition 2 relates to that 50. And what would you write for condition number 2? Condition 2 is less than 10% of the population is sampled. So we'd have to assume that this company that makes hot water heaters makes at least how many hot water heaters? Because we're going to take a sample of 50. So we have to assume that that sample of 50 is what to the population? And what would we write as an answer in this part? Yes, Tab's got it right there. So we'd say that the sample of 50 is less than 10% as long as they make at least 500. I know it's counterintuitive because you're like sampling more is better. And there are some minutiae to this, some interesting stuff, that when you oversample, your statistics actually get worse. You create more error. Now, we won't get into the statistical theory on that, but you can remember that sampling less than 10% is the condition. So we want to sample less than 10%. So if we say the sample of 50 hot water heaters is less than 10% of all hot water heaters, we are good. And that seems a reasonable assumption with this right here. Last but not least, what is condition 3? Remember, we're doing sample proportion. We just highlighted a moment ago what condition 3 will be. What is condition 3? Success, failure, you got it right there. So we need at least 10 successes and at least 10 failures. Since we're doing the sampling distribution of the sample proportion, it'll be NP and Q. NP and Q. So think about this. If we have 50, which is P, oh my gosh, I was looking over the other one. And we have 0.25, which is P. There we go. P is the true proportion of hot water heaters that will last 10 years. P is the true proportion of hot water heaters that will last 10 years. And that's what it says on there. 50 is our sample size, making it N. What is Q? If P is 0.25, what is Q? Q is equal to 0.75. Let's see who said it in the chat. Nice job, Jade and Dylan, great job. So P and Q are 0.25 and 0.75 respectively. So can you figure out what P and Q are? Because the success failure condition says that NP and NQ both need to be greater than or equal to 10, which gets confusing because we just did the less than 10% condition. Now this is that we need to have at least 10 successes and at least 10 failures. So NP would be, and I'm going to write it right here, NP would be equal to, we'll write it out, 0.25 times 50, which is equal to 12.5. And what's interesting is NQ will actually be 37.5, and that's just going to be 0.75 times 50. Does everyone see how those can be found? 0.25 times 50, 25% of 50 is 12.5, and 75% is 37.5. And interestingly enough, both these numbers add up to N, because you'd expect this many successes and this many failures. So people keep asking me, why do these conditions matter? They say, Brian, why do any of these conditions matter right here? Here's why. Binomial applet Iowa. Now, we don't use the binomial distribution, but I want you to see something. Many people haven't seen this. If P is equal to 0.01, we'd only expect one success. If it's equal to 2, 3, 4, 5, 6, what do you notice it's becoming as we get to 10 successes? At 10 successes, the distribution actually looks kind of what? At 10 successes, which is what we have, it says here on the binomial we'd expect 10 successes. That's the expected amount of successes, or the mean of this distribution. You can see it looks kind of normal. That's the whole reason we're doing these conditions, to use the normal. But if we don't meet the success failure condition, does that look normal? Is that the normal curve? Does the normal curve have a right skew like that? That doesn't look normal. How about here where we'd have 99 successes and 1 failure? Now it doesn't look normal. How about here where we have 60 successes and 40 failures? That's a perfect bell-shaped curve almost. It's not perfect, but it looks pretty good. Now we're not using the binomial, but just so you can see the whole point of these conditions, if we fail them, we can't use the normal curve, and if we pass them, we can use the normal curve. That's why we're checking conditions, is to see if the distribution is normally distributed. So it works on other distributions too that have very similar conditions for them. But people always say, why does this all matter? And I say, so we can use the normal, so we can use the 68, 95, 99.7 rule on it. To be able to know the mean and the standard deviation, we need to pass the conditions. We just did that here, random 10%, success failure. And now it says we need to find the mean, standard deviation, and the shape of it. Remember, if we pass the conditions, we'll do that. That's in the last video, Elizabeth. You might need to check out the last video. We went in depth on that last video. So I hate to push you away from the live video now, but check out that last video. We did it. You'll see me drawing it out, and I'll explain the differences. So we'll be asked if it's normal or not normal curve. If you pass conditions, it'll be normal. We won't really deal with unnormal curve or not normal curves, but now we know the shape of the sampling distribution. We don't want to use highlighter on that. The shape of the sampling distribution is normal if we pass the conditions. And then what will be the mean of it? Well, we're doing mu p hat equals p. And if you remember just a moment ago, I marked what p was. I'll draw p a little better than that. There we go. P was 0.25. Literally your answer. This is what it's asking for. I'm going to underline it in blue. It's asking for that, but the answer is p. It's saying what is the mean for the sampling distribution of p hat? And the answer is p. Now the harder part is the p times q over n square root. 0.25 times 0.75 over 50 and square root. I think it's 0.06 something. It's 0.06 something. Doing this one earlier. 0.025 times 0.75 p times q over n square root. And there it is, 0.06124. Nice job. Thank you in the chat for the help too. 0.06124. You got it. Do we make an error here? We got it. I think there's a star on that. As long as I think that's correct. And this is SD p hat, and it's equal to p times q over n square root. Please read what this says. This says the sampling distribution for the mean for the sampling distribution of p hat. The standard deviation for the sampling distribution of p hat. What are the other acceptable choices for C if it wasn't normal? We wouldn't get into that. It's a really good question. You can't use the normal techniques then it would have a right skew and probably applets. Good question, Daniel. We'd probably use an applet because the applets can accurately draw all of them, not assuming normality. So there are advanced ways of doing it, using non-normal curves to model these distributions, but great question. Suppose that after 10 years, we got some notation, get ready for it. Here we are. After 10 years, 16 out of the 50, wait a minute. 50 is our what? I need to hear it in chat. I need to know you're following along. 50 is our what? No Red Bull today, soda today. 50 is n. 50 is our sample size. So we now know what the sample size is. Good to see you, Chris. We have n, and what is 16? So Brock, we got that in the last video. Check it out, check it out. And actually, let's write that right here. That's what x is, and I'll show you. You might need to pause it. I'm going to show you when to use success failure in large enough n. Success failure in large enough n are when, I'm going to move my head out of the way, large enough n is for sampling distribution of y bar, success failure is for sampling distribution of p hat, and success failure is also for one sample proportion confidence intervals. It is in the last video, and I go more in depth on it in the last video, so check out the last video from earlier today. Quick question, what's the difference between success failure and NP? Good question. So right here, in this one right here, you know P. So in this one you do NP, NQ. But in this one you don't know P, so you use NP hat, NQ hat. When we make a confidence interval, we don't know P, so you use NP hat, NQ hat for a confidence interval. But if you know P, you use NP, NQ for the sampling distribution because you know it. So in a confidence interval, we're trying to estimate the truth, but with the sampling distribution, we actually know the truth. So when you're estimating the truth and you don't know it, you use NP hat, NQ hat. And when you have the sampling distribution, you use NP, NQ because you know the truth. If you know P, you can use P, but down here you don't know it because you're estimating it. I hope that makes a little more sense right there. No. You guys crack me up in the chat. Okay, using your answers from above, calculate the z-score for this observation. The formula for the z-score is observation minus mean over standard deviation, i.e. we observe, let's go back to black, let's take the marker right here, observe p hat minus p over the standard deviation of p hat. Now if you notice this is on the formula page, so let's plug in our values here. Our p hat from above was 16 over 50, so 16 divided by 50 equals 0.32. And we're going to do p hat is equal to 0.32 minus, right here, what is it, 0.25. These are all just taken from when we put our notation on it. And then we're going to divide right here, divided by 0.06, what was it, 134 I think, 134. Observation minus mean over standard deviation is the z-score, and I got it wrong, it's a 2 there. There we go. So all we're doing is standardizing this difference. That is all a z-score is, because we want to see if this is unusual. Observation minus mean over standard deviation. And what do we get? We get a z-score of 1.143. I think we can do that one next. I think we can do the true-false next. 1.14. Please tell me if I make any errors. I am going quickly, and I hope you can always pause the video. You can always rewind and keep asking those questions. The true, false at the end of practice exam. There are no videos for the first three. Let's do that. We'll do that very next. Given your answer, would you consider having 16 or more unusual? And the answer is what? The answer is no. That looks like I'm marking a wrong answer. The answer is no. Why? Because a z-score of 1.14 is not unusual. And usually we like to put the z-score way further out. Like if this had been a z-score of something like 10, that's ridiculously unusual. If it had been a z-score of like 1, not unusual. So the z-score of 1.14 is very close to what we expected. It's not more than 2 or 3 standard deviations, and either one of those is fine because 2 is unusual and 3 is very unusual. It's just kind of what do you consider unusual? 2 is pretty unusual. 3 is very unusual. Just to put that in context, a guy who has a z-score of 2 is 6'3". That's pretty tall. A guy who has a z-score of 3 is 6'6". 6'6" is very tall. So it's like the taller you are, the more unusual you are, and the higher z-score. But we were looking at, you need to look at the z-score right here. Is this unusual? Because this is just a z-score, and that is not unusual right there. So 16 has a z-score of that right there. So that's the z-score of 16. That's the z-score right there, and that is not unusual. Let's do those true falses. Okay, true falses right here. Okay, increasing the sample size will increase the margin of error of the confidence interval. Let's look at a confidence interval right here and see if this works. We have right here p hat plus or minus z star p hat q hat over n square root. There's our confidence interval, p hat plus or minus z star over p hat, q hat, n square root. Where is n? N is right here. Where is the margin of error? Right here. It says it will increase the margin of error. Wait a minute. If I increase n, that makes it dividing by a bigger number. If I increase n, what happens to the margin of error? If I increase n, the margin of error decreases. So this is definitely false. This is 100%, nice job tabs in the chat. You got it. This is false because n is what we're dividing by. Since the margin of error has n over here in the bottom part of the equation, it's going to make it smaller because as n gets bigger, it decreases. So as n increases, your margin of error gets smaller. The margin of error in a confidence interval is half the width of a confidence interval. Here's a confidence interval. Here's the width of it. It goes from, I need more room to write. Let me try to zoom in a little bit more and get a little more room. Oh, way too much. I don't know why it does it so quick. Let's draw it down here. Here's your confidence interval. And your confidence interval goes from, I want to make it symmetric. Your confidence interval goes from, let's say lunch is going to cost between $6 to $8. What is the width of this interval from 6 to 8? The width of this interval, what is the full width of this interval? The whole length of this interval is what? If you looked at the whole, it's 2. So the whole length of this interval is 2. Okay, so that's 2. What is half the length of the interval? So wait, and that's the margin of error. So this interval can be 7 or 7 plus or minus 1, and the width of the interval is 2. So is the margin of error half the width of the interval? Is that true? A margin of error is half the width of the interval? Is that how it works? Looks to me how it works. That answer is true. The margin of error is half the width of the interval. So the margin of error in a confidence interval is half the width of the confidence interval. Very, very true. There is no way to achieve a more precise confidence interval without decreasing the confidence level. So when it says precise, it says narrower. What did we just find out up here? That if you increase the sample size. Now here's the thing though. Some people have came to me and say, wait a minute. If you precision and confidence go conversely. If you increase the confidence, you make the interval wider and less precise. But it's saying narrower. So it's defining it as a more narrow confidence interval can only be found by decreasing the confidence level. The confidence level controls the z-score. When you look at p hat plus or minus z-score, the z-score in the confidence interval controls the confidence level. So it's saying this right here is the only way, if you manipulate this number, that's the only way to change the margin of error. You gotta look by my head. Is there another way to manipulate the margin of error that would decrease the width of the interval? You can increase the sample size too. So also the sample size is the only other thing we really can manipulate. P hat and Q hat have a say, but we don't, those are just things we'll find. We can't like increase P hat or decrease Q hat. They do control the width of the margin of error or the width of the interval via margin of error, but that's got it right here. And so this would be false. Comment cards at a restaurant are an example of stratified. Comment cards would create what kind of bias? Who's got what kind of bias? We'll do one more question after this, then I'm going to head off. What kind of bias would comments cards create? Maybe convenience, maybe non-response. I'll take all those. There's maybe people who, I was thinking of a different one. This is kind of an open-ended question. Hint, it's not stratified. That's false. Stratified is not comment cards. Voluntary, Garrett, you are right. I was thinking Garrett, are you in the class now? I think I remember it. I see all the names. I'm like, is that a current name, or am I just glad to see people back? But comment cards would be voluntary bias, which kind of creates a non-response bias too. This is kind of an open-ended one. It is kind of convenience too, because you're just putting them on tables. You're doing it in an easy way, not getting a good random sample. You're like, man, everyone who responded to the comment cards was so happy. And it's like, maybe it's just people who are happy are more likely to respond and they're more likely to volunteer. And it's not, it's got some non-bias, it's got voluntary, it's got all these issues. That is a sampling method totally full of problems. So people are saying true. This is false, right? I mean, you're saying true to what I'm saying, right? I'm like, okay, good. So we're like, no, that's true. I'm like, wait, that's not true. It's not stratified. You're not stratifying there by anything. You're not, and you stratify, you acknowledge a difference. So I think we're good because I see true in the chat. So unless there's a, yeah, good deal. Key says false on there, right? Hard tack. So what do we have last but not, oh, are people saying true for the last one? Oh, that's what you guys are doing. I'm pretty sure it's true too. That's what people are doing. I was like, wait a minute, what is true here? So when we look at this, I've already outlined what is going on with this problem. And do a review over this, how large enough works. I might still have the things we did earlier. I think they're here. No, we gotta find them. I got too many things open. Did we did it earlier today. Did we do it over, well, I'll be. And here we are. This is where I did it. Here are the conditions, so you can always pause the interval. There we go. And so here it is right here, the difference between success failure and also large enough n, that the three things you need to do, and let's do it on this question, is we need to look at the shape, we need to look at the amount we need for that shape, which I kind of call the rule. It's just an amount you need, and then you need to see if you meet it. Okay, so I want you to say it in the chat with me. Let's see if we're passing the conditions right here. Okay, so how is this distributed? You can see I've highlighted in my answer. How is this distributed? This distribution is what? How is this distributed? This is distributed howly. How is this distributed? Normally. So since it's distributed normally, what is the rule how much do we need as a sample? Since it's normal, we need how much as a sample? If it's normal, we need what? 1. If you notice, the more skewed it is, the larger n needs to be. So it's kind of a moot point, because if it's normal, we're good. So is 2 large enough? Is 2 large enough when it's normal? And that's the key. It's when it's normal. You have to look at the shape. Remember, look at the shape, look at the rule, and then do we pass it? And the answer is 2 is large enough because it's normal. So if it had you write it out, you'd have to say like, well, since it's normally distributed, 2 is large enough. You guys crack me up in the chat. I think there was like one more. Will you do the confidence interval question above this? Okay, we got this. Let's do it real quick. Let's do the confidence interval question. Interpret your confidence interval. Let's do a quick confidence interval. You ready? Okay. What was p hat? What was p hat? Condition 1, condition 2, condition 3. Here we go. It is generally believed that 75% of college sophomores regularly recycle. You go out and you talk to how many college sophomores. There we go. Here's the confusing thing. This is your sample size. This is your x. This is x. This is n. We're doing this one very quickly. Just sorry if it's a little quick here. Remember, you can always review this. Test is coming up soon. But n is 128 and x is 84. So 84 over 128 is equal to what? 84 over 128 is equal to what? 84 over 128 is equal to what? What am I solving for right now? I am solving for what? This is equal to p hat. Because that is the sample proportion of people who recycle, the sample proportion of sophomores who recycle. 84 over 128. I'm going to do it quickly, no mistakes. Let's do it. 65.625. We're going to 0, 6. I knew I was going to be blocking it. 65.625. There we go right there. The number we just saw, that is p hat. So we have just solved for p hat. So now we can actually build our confidence interval. If you notice, we'll always give you the z-scores right here. So we have here a 93% confidence interval. The equation is p hat plus or minus z star p hat q hat over n square root. How are you going to find q hat? To find q hat, no scantrons. To find q hat, you're going to take p hat and go 1 minus p hat. That is q hat. Nice job, Chris, in the chat. 1 minus p hat is q hat. That's all we are doing right here. And so now we go right here, and I'm going to abbreviate these numbers just for brevity's sake. Carry out your numbers on the test, but just my handwriting's sloppy, and I'm going to do it in the calculator. 0.065, and let me see that number again. It was, yeah, wasn't it? Yeah. Okay, well, 6. 0.656. And then the next one is plus or minus, the z-score is right here. So then we put the z-score in of 1.812, and then we have to put the whole radical right here, and we have to go 0.656 times 3, and then 44, is it going to be? I think so. That is correct. I'm solving it in my head right now, but let's look at this again. 1 minus... I was doing that yesterday too. There we go. That rounds up to 3.344, and so that's the answer there. And then we take this, and we have to do it over 128. 128 was the sample size. We're going to double check. Don't want to get a problem wrong. 128, I identified as n as the start of my problem. Know your notation. So all we have to do is solve this interval right here, and we are good. Let's solve it. So we're going to do p hat times q hat. There's p hat times q hat over n square root. And now we found the standard error. We times that by 1.812. And what did we just find? We found this right here, which is the margin of error. We have now just found the margin of error of our interval. And now since we found the margin of error, we're going to take this and we're going to go 0.656 plus the margin of error. We get the upper, because all I'm doing is doing the plus or minus right here, right now. So that was the upper. The upper is 0.732. And then the lower of the interval, I have to take 0.656 and subtract the margin of error. 0.656 minus the margin of error. So that'll be 57. It rounds to 58 right there. So let's just put that in right here, 0.58. And there it is. Last but not least, and I think we have it up here, and this is such a great place to end. Last but not least, we need to interpret this interval. When we interpret our intervals, and we should have it still on here somewhere, when we interpret our interval, there's the topics over the test. Do we still have it? We do. I am, and if you remember, I think it was it 59? Let me look at those numbers again. The numbers were, we did it on the slide. 58 to 73.2. Okay, 58, 73.2. The easy part is putting in the numbers right here. This is the easy part. I am 93% confident the true proportion of sophomores who recycle at the University of Tennessee, if that's where I got our sample, is contained in the interval 58% to 73.2. And if you do it as a decimal, that's all right too. But this part right here is where people make mistakes. But remember, it's the true proportion of sophomores who recycle. I am 93% confident the true proportion of sophomores who recycle is contained in the interval 58% to 73.2%. And we've kept this up here since we first learned confidence intervals, and we use it for every problem to interpret them correctly each time. That's got it. Any last quick questions? I'll take like one more, two more. I don't have time to do a full question because we'll be heading over to the room here soon. Remember, it is at 6:30, but I meet up with my TAs and everything. Random question, how do you solve for n in a confidence interval? When you solve for n in a confidence interval, you would have to go in, to solve for n, you have to go here, and n, depending on what you have, let's go here. The margin of error in a confidence interval is as follows. Reason being is the confidence interval is p hat plus or minus z star p hat q hat over n square root. So depending on what you know, well, one, this part of the equation is actually meaningless to us because we're probably going to look at the margin of error. So the margin of error is equal to, if you were to know something like the margin of error was equal to 0.04, and if you knew p hat, then you could go and z, like if it says z is equal to 1.96 and p hat is equal to 0.8, and then q hat would be equal to 0.2. So you could go here and take everything and you have some fun ahead of you. You have algebra. Yay, algebra. So from here, it's simply solving the problem to solve for n, and that's got it right there. So now it's a reduction algebra problem, which you can just work out, you can double check. I have no idea what the answer, I made up these numbers, but the only way to really solve for n is if you have the numbers right here. There's a lot of other ways, but this would be one way right here. What's the difference between a convenience and a random sample? Convenience is like taking the first 50, but if you randomize like we did last night on the Kahoot, taking the first 50 would be then random. Taking the first 50 would be random if you had like randomized them. First 50 randomly is still random if you take numbers and jumble them up. We mentioned last night if I were to hand out numbers in a hat and say everyone who gets numbers 1 through 10 is a winner, well, you're drawing the numbers randomly. Even though it's the first 10 numbers, it's still random. But if I looked at the people who came to class and I said, okay, the first 10 people in class take my survey, and the first 10 people walk into class take the survey, that's the first 10 in terms of convenience. The steps for taking a random sample, simple random sample, would be enumerate everything in the population, and then everything gets selected randomly. You select random numbers. If you order them, it still is random if you give everything a random number and then you select the first. I know it's confusing. That is a tricky question we've asked before. But is that it? We don't try too many tricky questions on the test. That's not our goal. So most of the questions are super straightforward. So far, I've been looking at what people have been doing, and I feel like it's a very good, straightforward test. Any other last questions? We've got time for like one or two more. We covered a lot of the tricky and the hardest ones. Definitely know how to do what we've been doing for the last few days here. We've been doing a lot of great review, and thank you for tuning in. This is going to do it. It's time to sign off, and I'll be seeing people at the exam tonight. So, good luck. We'll end with some Rick and Morty today. All right. We'll end with Jason Cam. It's a bummer.
Like TV from other dimensions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.